Hello guys, nice to see you.
Hello.
Good afternoon.
Hi. So last time we focused our attention on introduction of sound waves as longitudinal waves in the some elastic environment. Yeah, good afternoon. Hello, everyone. So that elastic environment could be gas or liquid or solid environment. Sound waves can spread in all of these environments. And we introduced the relationship between pressure and displacement of some air, or let's say environment, small element, which happens parallel to the direction of sound wave propagation. And we derived equation for the speed of sound. So today we proceed further with our analysis, and we will discuss questions related to intensity of sound wave, and also how some new units for operating with intensity, like decibels. So it's kind of not intensity itself, it's so-called level of sound. And we will discuss why we use this type of parameter, not just specify it in watts per square meter, for instance, and also some basic features which should be known in terms of threshold of hearing and some already level of painful feelings. So we will underline this and also specify how frequency of sound effects on our perception of sound level, means sound intensity. Okay, so let me switch the camera. Oh, okay. Oh, now it works. That's good. And one thing which we need to recall before we proceed further with the derivation for intensity equation, we wrote during our previous lecture that change in pressure, so this is capital P, is equal, so we derive this equation, we are taking derivative of the wave equation, was equal to minus, sorry, we don't have minus here, final equation. So it was B bulk modulus times K, which is wave number, times S maximum, means amplitude displacement of gas element with respect to equilibrium condition, times sinus Kx minus omega E. So we can write from here, we also did that previously, just recall it, P, delta P is the maximum, like amplitude deviation in pressure, is equal to B times K times S maximum. So we keep this in mind. Also, we need to write down the equation which we derived for the speed of sound, and that was V is equal to square root of B divided by rho, which is volume density of the environment. And now, taking this into account, we can express B from this equation. So that would be B is equal to rho times V squared. And why we are doing this? Because it's more common to operate further when we deal with with sound intensity, with density of environment, not with its bulk modulus, since density is more common feature and it's easier to be measured. So now, if we substitute instead of bulk modulus here, its expression in terms of density and speed of sound, we get the following: delta P max is equal rho times V squared times K times S maximum. And one more step here we need to do. As you remember, K is equal to 2 pi divided by lambda. So if we now multiply and divide by frequency, we will have angular frequency in the numerator, and lambda times frequency is speed of sound in the denominator. So again, we substitute K with its expression. So we end up with the following equation. It will be density times V, because we cancel this square and this V in the denominator, times omega, which is angular frequency, and times S maximum. That is maximum displacement. So in this case, we expressed change in the pressure in terms of density and speed of sound, instead using this bulk modulus B, because both density and speed of sound can be easier measured and are commonly available information. So that's why we can express delta P with this as maximum, like prefactor before sinus. Sinus kx minus omega t. Okay, now we have this, and we can proceed further in derivation of intensity of periodic sound wave. So let us go to another slide. And again, consider our already familiar system. We have some tube with a piston. So this piston is moving back and forth with some angular frequency omega. And also we have some small element, air inside this tube. dm also moves back and forth. So with some speed Vx, because of motion of this piston. Now we want to get the power which is transmitted through this pipe. it's kind of one-dimensional case along axis X. So means amount of energy per unit time. We can express this P, let's mark it P power. So, or maybe we can just write power and that's all. It will be, in order not to confuse with pressure. Let's write power is equal to the scalar product, like dot product of force vector times velocity vector, Vx. So work done by force is scalar product of force and displacement. And power, displacement divided by time. So that is speed. So now, let us write it in terms which are relevant to sound wave, because this is quite general expression for power in terms of some mechanical models. So power for the case of sound wave should consider change in pressure, delta P, as a function of position and time, cross-section area of this pipe, so it would be A. Then that is actually magnitude of our force, delta change in pressure times area, and we multiply by unit vector I to specify this as force vector. Then we have dot product with the velocity vector Vx. And in this case, that's actually partial derivative of our wave function, which describes displacement of oscillating small element of environment, in our case, gas, over time at some fixed position x. So we have d, and here we have s as a function of x and time, position and time, times unit vector I to specify that this is displacement vector over dt. So that is kind of derivative of displacement over time at fixed given position x, and that gives us stands for the velocity vector. So now we know that for sound, which is longitudinal wave, displacement of elements of environment happen in parallel direction to the direction of spreading the wave. So that's why this force vector should be always parallel to the velocity vector. And in this case, we can skip these unit vectors because if we have angle equal to 0, cosine 0 is unity, so we don't need to deal with them. So we will operate only with amplitude of this scalar product. So now let us write expressions for change of power and expressions for displacement, both as function of position and time, in the scope of this equation for power. So for pressure, we already discussed on the previous slide that we can express it in terms of, instead of bulk modulus, density and speed of sound. So we can write rho times V times omega times A, which omega is angular frequency and A is area, times S maximum. And here we will have sinus kx minus omega t. So that is expression for our change in power times area of the pipe where all these processes are happening. Then we have product. We multiply by the partial derivative of S as a function of x and t over dt. So let us write it. We have d over dt, and here is S maximum times cosinus kx minus omega t. Okay. So we have our equations we need to deal with. We remember that derivative of cosinus x is equal to minus sinus x. And with this in mind, we can proceed further. So we have our first term, which doesn't change so far, rho times V times omega A S maximum times sinus AX minus omega T times, now we need to take derivative. So it will be first derivative of cosinus will give us minus sinus, and then we need to take derivative of the argument of this cosinus and multiply by it. So that will be x is considered as constant. So derivative of argument will be minus omega. So we have one minus from taking derivative of cosinus, another minus from derivative of the argument. So we cancel out these two minuses, and that will end up in S maximum times omega, which is the derivative of our argument of the cosinus, times sinus kx minus omega t. Okay, so now when we multiply these guys, we will get the following picture. It will be rho times V times omega square times A times sinus, S maximum square and times sinus square kx minus omega t. Okay, so this is equation we will continue working with. So far, everything is clear, yes? Okay. Now we need to take some average because you see that this is function of position and function of time. We don't care about position so much because we can pick up any position, assuming that we don't have like attenuation of this sound wave. It will be the same power transmitted with sound wave at any position along x along this pipe. So we can pick up some fixed position. And convenient would be to pick up, let's say, x equals 0. So to make it easier for us. And we have this time dependence. So it tells us at every given moment of time, these equations provides us information how much power is transmitted. Since it's kind of could be useful information, but more practical information is to get some average amount of power which is transmitted, and in that, for that purpose, we need to take average value of power in the time interval which corresponds to the period of this oscillation t. So let us go to another slide. If we have some function, let's say f as a function of x, and we want to take some average of this function in the interval from a to b of this independent variable x, that is defined as 1 divided by b minus a. So it's just length of this interval of change of the independent variable, integral from a to b of our function f x dx. So that is general definition how we can get some average value of a function. And obviously we need to consider this instead of this function, arbitrary function fx, our function of which we derived on the previous slide, which is power as a function of time, because we assume x as constant, x is equal to 0. So let us rewrite this equation in a new slide, taking into account that x is equal to 0. So that will be kind of starting point. So power is equal. So what do we have there? Rho omega a square, rho v omega square times a times s maximum square times sinus square. And here we consider x equal to 0, so we can write just minus omega t. Okay, so that is the case when we need to take the average of this function. So since this is constant, we don't care much about this. We just keep it in mind, but we don't need to integrate it because it's just a constant. So only part we need to integrate is this, which is actually function of time. And we want to get average of this term of our equation, and then multiply by our constant. That will give us average power. So that's why when we need to consider 1 divided by period t, which is interval kind of from A to B for independent variable t. So from interval is our period times integral from 0 to time our period t, and then we have sinus square minus omega t dt. So that will give us average value of this term in the time interval from 0 to capital T, which is the period of our sound wave. So let us consider some properties of sinus. So sinus minus x would be defined as minus sinus x. Keeping this in mind, we can write that sinus square minus x is equal to sinus square x. Because if we take this to second power, minus and minus will cancel. And that's why we can, instead of sinus square minus x, consider just sinus square x. So that's why we can kind of neglect with this minus in our argument. So we can even like delete it here and consider sinus square omega t dt will be more convenient. So now, another thing, because we cannot integrate this sinus square, there is a trigonometric relationship which can define sinus square x as 1 minus cosinus 2x divided by 2. So now instead of sinus square omega t, we will apply this transformation and we will get the following. So that will be equal to 1 over period t and 1/2, which is coming from this 2 in the denominator of this transformation, integral from 0 to period t dt. So that is this unity. Then will be minus. We will have here again this 2 from denominator here. Then we will have integral 0 from 0 to time interval, like the period of the wave, times cosinus 2 omega t. We had omega t, we need to add 2 because we have here 2 in the argument of cosinus. And that we had dt, but in order to integrate, we need to adopt our argument of cosinus with the format of our differential. So we want to have not dt, but d to omega t. Since omega and 2 are constants, we can do this. So we can multiply our differential by 2 omega, and we get to omega t. But if we multiply here, we need to divide also to get the same. So we need to add 2 omega here in denominator. So now we can integrate this, guys, and that will be equal. So we have 1 over t times I'm over divided by 2 from 0 to t capital minus, here it will be 1 over t times 1 over 4 omega. And when we integrate cosinus, we get sinus. So this will be sinus 2 omega t from interval 0 to t, capital T, which is period. So if we substitute here capital T instead of time, we cancel out this t in denominator. So we will get just 1/2. Then we have minus 1 divided by omega 4 omega capital T times sinus 2 omega period T. And as you remember, period, like product of this, maybe we can clean this part. We don't need it anymore. As you remember, omega t, that will be 2 pi divided by period t, that stands for omega, times t. So we cancel out t and we get 2 pi. So if we have this 2 pi multiplied by 2, it doesn't matter. Means that this term of our integral will be always equal to 0. So eventually we get that average value of this function, or this one initially we consider with minus, in the time interval from 0 to period will be equal to 1/2. So keeping this in mind, we need to multiply this constant in front of this sinus square minus omega t just by 1/2, and that will give us average power transmitted by sound wave in the interval of 1 period. So let us write it down on the new slide. So power average is equal to 1/2 times rho times V times omega square times area A times displacement, maximum displacement square. So if we consider intensity, which is per unit area, we need to divide this average power by area, and that will give us 1/2 rho times V times omega square times S maximum square. So we see that intensity of sound increases linearly with density of the medium and speed of sound in this medium, and increases in second power from such parameters as frequency and kind of amplitude of air element displacement. So taking into account that delta from our first slide initially at our today's discussion, we wrote that delta P maximum, change in pressure, maximum pressure, is equal to rho times V times omega times S maximum. Then we can express this product omega times S maximum, omega times S maximum. That will be equal to delta P maximum divided by rho times V. And now we see that we have this omega times S maximum square. So that's why we can express our intensity of the sound wave as following. It will be 1/2 times density times speed of sound. And instead of omega times S maximum square, we can put delta P maximum square divided by rho square V square. So we can cancel these guys. And eventually we can express also intensity in terms of change of pressure, like maximum pressure, amplitude value of pressure in air. That will be delta P maximum square divided by 2 rho times V. Okay, so these are two equations which describe intensity of sound, periodic sound wave, and you guys should better remember them. So this derivation, as we discussed at the beginning, was done considering one-dimensional case when we have some pipe and sound wave is spreading along this axis X, which is parallel to the pipe. However, that is some model situation. Usually we have point sources of sound. Let's call it source. Can you please show previous slide at the end? Yes, sure. So here we have two components of integral. One component gives us 1/2, another is 0. Okay, you're welcome. So if we have point source, then sound will spread radially. It will spread to so-called space angle 4 pi steradians. So that will be, so we draw here some circles, but indeed it's like these are spheres. We can represent it like this. So in this case, these circles, which are projections of like cross sections of spheres. These are surfaces with the same phase. For each point on this surface, the sound wave possesses the same phase, and distance between the two neighbor adjacent surfaces, this is lambda, so means distance between two adjacent regions with the same phase is defined as the wavelength of this sound. And also these radial directions, which go outwards from the center, like this, they define the direction of sound wave propagation and are called rays. So now if we consider intensity of such sound, we need to divide not by just cross-section area of the pipe as we considered earlier, but we need to divide by the area of the sphere, because if, for instance, we want to define intensity of sound at some distance from the source, which is equal to small r, some radius of this sphere. So in that case, intensity will be equal to some average power, average of this point source, divided by 4 pi times r squared. So that's how we determine intensity if we know the average power of the point source at some distance r from the source. We need to divide by the area of the sphere surrounding this surface at this given distance. Okay, so I see that with this we can finish our discussion today. We will consider sound levels already. That's not much. We will consider it during our next discussion on Friday, and we'll finish our, on Friday, we will finish our topic sound with considering Doppler effect and shock waves, which are formed in environment with bodies which move with supersonic speed. So we should divide to all area. Yes, we assume that our environment in which this sound source is located is isotropic. And that's why, since it's isotropic, means the properties like densities and this bulk modulus is uniform in all directions for each of these rays. We have the same properties of the environment. Then our waveform with these surfaces with the same phases will have shape of a sphere. And since we have a sphere, we use area of the sphere in denominator. And that's why we distribute all power, which is produced by this sound source to all area of the sphere at given distance r. So depends on which distance we want to measure intensity. Obviously, that it will significantly reduce proportionally to 1 over r squared as we go further from this point source. Okay, so, oops. Yeah, you are welcome. If you have any additional questions, you are welcome. Let me change back the camera. If everything was clear, then see you on Friday, where we will finish our discussion about sound waves. And until then, take care and have a good day. Bye-bye.
Goodbye, thank you.
Thank you, goodbye.
Mm-hmm.